Hi, my name is Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome, this 11th of January 2026, to O-Day, Brewing Tea, by breaking the ideal gas law. How is everyone out there in the YouTube's land? This wonderful, frosty Northern Hemisphere day. We're about -10 here. I don't know what it's like in your part of the world. If you're Antipodean, enjoy the summer. Hello, Overwound Games. Just a Guy on a Donkey, Brandon B5075. Austin Summerall, -K2K. Hi, Artifact. Artifact has been doing some wonderful updates to his incredible data acquisition tool. I'm sure you'll see some more about that in the near future. Hi, Ava Labs. Hi, Weed Nerd DWC. Yoni6177. Estonias is in the house as well. Ken Pratt too. Sorry to keep you waiting. I had to reset up everything here in the office and make sure it was working, so we didn't have a 8-minute of silence at the beginning of the video. I'm presuming, of course, you can actually hear me now. It would be silly if that wasn't the case. Hello, Joseph Collar. Corky Goss is also in the house. Mr. Anders Chauxis. There we go. We've got the Antipodians here. Nick Moore. Great to have you. Excellent. You can hear me. So I had a lot of fun putting this one together this week. I had a question many moons ago about how processes could occur in biological systems. And I don't know if you remember, but I looked at the work of Vladimir Vysotsky and Ada Korninova, and I think it's called Scooby-Doo. It's talking about something similar to one of those scobies that you make special tea from. Not the tea that we're going to be talking about today, but sort of brewed tea in a different way, where they have yeast and bacteria and so on, and it makes a rich, supposedly healthy brew, or water that you can drink. And that team, so Ada Korninova is in Moscow, and Vladimir Vysotsky is in Kiev University, good friend. And they showed that they could take deuterium oxide, heavy water, and glucose, and methagenic sea ooze, and they could take manganese 55, and the bacteria would produce iron 57 by taking a deuteron and putting that inside manganese 55, which is a single isotope. Deuterons, if they're all there, that's a single isotope. Beautiful system for coherent energy transformations. And iron 57 is the rare isotope of iron, and it has this NMR moment, and so they could detect the fact that it had been produced in that system. And they also found that they could do, I think, one half-life in about 2 weeks, something like that. I think it was right, maybe I'm thinking of something else, but they could accelerate the remediation of cesium-137 salts by, again, using this syntrophic colony of bacteria and combining that with these cesium-137 salts, and the bacteria appeared to be inserting a proton into the cesium-137, making barium-138, and it decays and it makes a stable element. So for remediation of nuclear waste. Of course, there was Kervran in the 1950s doing the whole chicken study, where you have these chickens that don't have enough calcium in their diet, so they can't produce hard shell eggs, but he gives them potassium, and the chicken puts a proton into potassium. So the theory goes a bit like the other bacteria, or maybe it's the bacteria that do it in the gut of the chicken, and it produces calcium and they can produce hard shells. Of course, the amount of energy that these reactions produce should kill outright the bacteria and or the chickens, if it's the chickens doing the work, not the bacteria in the chicken's gut, at the behest of the chicken. Of course, the most extreme anomaly in this field that we have discussed over the years is something that the late Mahadevin Srinivasan shared at ICCF 20 in Sendai in Japan. And this was something he was sitting on for practically 2 decades because he was fearing for his reputation, the old reputation trap. And what it was this smelting, recycling ferrosilicon foundry in Coimbatore in India. And they had found that when they were putting scrap iron and silicon dioxide, like basically sand or scrap glass, with the, I think it was 11 megawatt 3-phase electric arc 3-phase furnace, they were finding they were getting 4 tons of excess metal a day. 1 ton of extra 1 ton of extra iron and 3 tons of extra silicon. And the energy release from that should be unbelievably fantastic and explosive, but somehow it's doing it. And this worked, I think it was something like 11 weeks, 24 hours, 7 days a week. It was producing 4 tons of extra metal. And they know the metal's not put in there, that the iron, they know the weight of the iron that they're putting in. They know the weight of the silicon dioxide they're putting in. So they know the weight of those elements that are being put in. Where are they coming from? And of course, if you've been following me long enough, carbon and oxygen fuses to silicon. So you've got 12 and 16, and they fuse together to make 28. And 2 28s make iron 54. There's other ways to get there, one of which I've discussed, and we're going to briefly touch on that today. Of course, the majority of carbon atoms are 12. The majority of oxygen atoms are 16. The majority of silicon atoms are 28. And so, in my view, coherent energy transformations are well suited if you can do this electronuclear collapse and driving things into coherence in these systems. So we're not thinking of brewing the kind of tea that I'm talking about earlier. I am talking about this kind of tea that you see here in this lovely lakeside view in the Lake District on this veranda. I could just grab that tea right now and slurp on it with those nice shortbread biscuits. What a lovely thought that is, with the spring flowers there sitting on the balcony. England really does have some beautiful views. And if you ever get a chance to go to the Lake District, I seriously recommend that. Now, one of the technologies that is often quoted as being something that coherent energy transformations needs to compete with is heat pumps. These are the sort of things that you have air source heat pumps or ground source heat pumps. Even an air conditioner is effectively a heat pump. And it's actually using this thing called the ideal gas law. And you have a refrigerant in there. In fact, your refrigerator works in a similar way to this. And you have something that turns to a gas and releases heat, but when you pressurize it into a liquid, it releases heat. And then when it goes into the refrigerator and expands, it then absorbs heat from inside the refrigerator. And it's the same kind of way that your air conditioner is working. And a heat pump is kind of working in reverse. It's absorbing the heat from the ground or the air outside and then ideally pulling it inside. You do need some certain level of temperature for these things to work. Typically, the one that my mother had installed in the UK, it was an air source heat pump, and it was more costly electricity-wise for heating when the temperature outside dropped below 5 degrees centigrade. But all the time it was above 5 degrees centigrade. There was a net benefit there, although minimal at the low end. However, she lives with the Gulf Stream coming up to the beautiful south coast of England, and so rarely does it get as cold as it is right now. So Boyle's law, as I show here on this slide, was formulated by Robert Boyle in 1662. And it says that for a fixed amount of an ideal gas at a constant temperature, the pressure P and the volume V are inversely proportional. This relationship is expressed as PV equals a constant, or P1V1 equals P2V2, meaning if the volume decreases, pressure increases, and vice versa. That is to say, if pressure decreases, volume increases. Now, the ideal gas law, PV equals nRT, is kind of like part of the same story. And if we switch that around, we can see that temperature equals PV over nRm. What is that? Well, P is the pressure, V is the volume, and we can see those things are in that relationship as per Boyle's law above. And then N is the number of moles of gas, and R is the gas constant, and then T is the temperature in Kelvin. So therefore, the temperature varies proportionally with the product of the pressure and volume, the PV, which is adherent to Boyle's law, and inversely with the amount of gas. Okay. So what does this practically mean in ordinary scenarios? Well, I've often talked about this thing where you pump air into a tire. You might have done this if you cycle a bike. And the tire gets hotter. Of course, that's because you've got more air trying to occupy the same space, and it's trying to get to the same sort of equilibrium with the environment, and so it releases heat. And it's a good way to think about, at least in some sense, what I'm about to show you on the next slide. Conversely, if you have, say, a gas canister and you press it, as the gas expands, it will cool. And there are actually, you will sometimes feel when you are holding a can that the actual can is cooling down. These kind of things occur. So, yeah. So what is relevant here is that if you imagine again that pumping the air into a tire, you're kind of, you're reducing the distortion of the air outside, because you're taking air from outside and you're putting it into a more confined space, and it releases energy from that to become in equilibrium with its environment. And this kind of is on the periphery of this phrase that I've quoted many times that was given to me in 2000 and I believe 14, when one Stoyan Sargachev, abbreviated to Stoyan Sarg, stayed with me here. And the phrase essentially was this: all energy release comes from a reduction of the distortion of the physical vacuum. All energy release comes from a reduction of the distortion of the physical vacuum. And the first time I really spoke about that phrase was, I think, in a presentation I gave in Copenhagen to the Engineering Society of Denmark in 2017. And it stuck in my head because essentially what Stoyan Sarg was saying is it doesn't matter if you are condensing from a plasma down to a gas, or a gas down to a liquid, or a liquid to a solid. all of the energy that gets released from those condensation processes is due to a reduction in the distortion of the physical vacuum. Now, if you have two chemicals coming together, like carbon and oxygen, making carbon dioxide, the yield you get from that chemical reaction, 5 electron volts roughly per molecule produced, that also is because those new arrangements of carbon and oxygen overall distort the physical vacuum less. This is the same when you have effectively a uranium-235 atom splitting into roughly 2 equal halves. The 2 halves themselves are more efficiently packed on average per nucleon, and so they release energy because overall they distort the physical vacuum less. That is true to say when you take 2 deuterons and you fuse them to 4 helium. In fact, that is a massive reduction in the distortion of the physical vacuum, because those 2 deuterons almost do the same amount of distortion of the physical vacuum as the combined 4 helium nucleus. And so that's why you get such a high yield per nucleon. Of course, the ultimate extension of that is the complete collapse of a baryon, a proton or a neutron, such that the proton does not distort the physical vacuum at all, or the neutron does not distort the physical vacuum at all, and so the energy release is total release, and it's 938 million electron volts, roughly, for, I think it's a proton. Okay? And you could kind of think of all of these things like a Casimir cavity. That is to say, you've got your Casimir cavity, you've got your 0-point energy, the photons or whatever outside, and as it comes together, it's distorting it less, and the zero interference with the waves in between, they're squeezed out, and you get that energy release. Well, I've talked about the concept of a Casimir well. That's what I'm calling it, for want of a better phrase. A bit like I refer to the gravitational well as my extension of the Middle Ages version of gravity, the push model of gravity, in that I'm saying that matter is condensed in this coherent energy transformation process in ordinary matter, and this results in a gravitational well, that is to say, a frame dragging of etheric clusters and relic neutrinos into the place at which the matter is condensed. So what is that? Well, it is to do with our structure here, and that the electrodynamics in the structure force matter into the cores and subcores of this overall structure, and sub-subcores. Okay? And you can see this actual process in the work by Metin R here in cavitation in water. This was at, I think, 23 kilohertz, and I would argue that this point here and this point here are functionally equivalent to this point and this point. And the reason you see these bubble structures coming in here and coming in here and coming in here and coming in here to this point is that this is the phase singularity and this is the anti-phase singularity. And this is a depressurization and a depressurization. That's why you see the bubbles. Okay? And so this is a point of pressurization and coherence here and here. And ultimately, you have, that's equivalent to this beam coming out here and this beam coming out here. But ultimately, that makes a very much larger vortex. And the vortex is pulling material in to this core. And the electrodynamics is producing the Aharonov bomb effect. And so matter that is of the same type, that is to say, if they are electrons, or if they are protons, or if they are oxygen atoms, or if they are aluminium-27 atoms, or they are sulfur-34 atoms, or you get the idea. They come into here, they are put into a coherent matter state, and you get a whole bunch. I mean, some doesn't quite make it, some isn't cohered, some gets thrown around to have another go at the process. But a quanta of material is cohered through the Aharonov bomb effect, and it is phase synchronized and energy synchronized into a coherent matter wave and wavelets and interfering, and you end up with what Svyatomenko called an electron, nucleus, nucleon macrocluster in here of coherent matter wavelets and waves. Okay? And I've gone into how all of these, when you increase the density here, then the strength of the gradient here, the ether gradient, the Casimir well increases. Now, remember what I said before. All energy release comes from a reduction of the distortion of the physical vacuum. So if you have a continuous flux of matter going in here and cohering into the same space, then there is a breaking of Boyle's law. That is to say that you can have more matter going into the same space-time because it's a coherent matter wave, but it isn't increasing the pressure. Do you understand what I'm saying? That means that you're out from the viewpoint of outside of this bubble, outside of this fractal magnetohydrodynamic structure, from the viewpoint, there is a constant Casimir well here. Like, the waves can come in and the matter can come in, but it doesn't need to be reopened to gain the energy. It's constantly coming in. So there's a flux. So it's like a permanently open but always closing Casimir cavity, because matter is constantly going in here, and the photons and everything with it. Okay. So with my presentation that I did before Christmas with our wonderful flying pig on his flying carpet, I talked about how protons and tritons, but tritons you need to make them first, and they don't. It's an isotope that decays with a relatively short half-life. Protons, other than tritons, are the most suitable, in my view, to create an enhancement of a gravitational vector in a core, and I'm arguing that effectively they cohere in this core here, and they focus the gravitational energy in that core. And so it's an enhancement process which gets stronger and stronger because you are spin aligning the nuclear spin of those protons. And this is what NASA was doing with Richard Eskridge and Amy Eskridge, and they found that by just using I think it was 0.4 of a Tesla neodymium magnets, with bismuth spin aligning, they could do a measurable amount of gravitational vector reduction, i.e. weight loss. And it's much better if you could do it with protons, in my view. And so they enhance the gravitational collapse. So what Matsumoto is talking about in his book Steps to the Discovery of Electronuclear Collapse is, and what Mikhail Solin is discussing in his 1992 quantum coherent nuclear reactor patent, is effectively gravitational collapse. And we know we've got coherent matter in there, and we know that because we have seen in our experiments and third-party experiments and in that of Matsumoto that more physical matter is coming out of the structure than can possibly fit inside it in its ordinary matter state. So even a child can work that out, that it must be coherent matter in there. Now, how that comes about is a point of what we're going to be discussing today. So as matter is condensed by the Aharonhof-Bohm effect coherence into a matter wave condensate, there is no typical pressure increase. No typical pressure increase. Now, you could argue that, well, basically, that you can achieve this incredible matter densities without compromising from a pressure type of point of view, the stability, the virial stability of these structures. Now, we know for a fact from physical observation of the decayed products from the Binge-Ren-Huang DHX2 reactor and other reactors, VCS5RT, etc., that these wheel within wheel within wheel structures have stabilities that are stronger the smaller the structure gets. So the third order n-2 level structures, you've got the n-1, n-2. The n-2 structure survives the n-1, and the n-1 survives the n structure. So their relative virial stability is increased the smaller these structures are. And they build, in my view, from the bottom up, and they decay from the top down. Okay? But it is the case that the coherent matter that is being aggregated into these cores and subcores, that is being first cohered and then aggregated in these cores, all the time it's in the state of coherence, it's not compromising from a pressure point of view in the same way that you might, if you're blowing up a tire, increase the pressure in the tire to a point, and maybe you've had this experience with a balloon. You get too much pressure in the balloon for the integrity of the confining structure to keep it there, and then the balloon bursts and all hilarity ensues. Well, in this case, you're putting more material into the same coherent matter condensate, but it isn't having that pressure destabilizing effect. Now, technically, the de Broglie wavelength of the matter wave in there may be changing. Someone with more quantum mechanics can maybe explore that idea. So technically there is a kind of temperature in there, but it's not manifested in the way that colliding particles are colliding when each of those particles are able to bounce off each other because they're not coherent. That is to say that as the net energy in the coherent matter condensate in the cores increases, it's still in that coherent matter state, because every time energy is in there, whether it's added to it or it's from a process that occurs in it, all of the energy is instantly across the entire condensate. And you only get the energy that was in it back when the structures collapse. So I'm talking about that here. All energy is shared between all members of the condensate, and therefore it maintains its coherence. And because it's maintaining its coherence, it maintains its virial stability. So the last point here is that the energy that is gained potentially in any particular reactions is released on the field collapse and the matter decoherence. Now, the point is, when the matter decoheres, it may not be the same matter that goes in. And you've got to, if you go and look at what S.V. Adamenko says in his 760-page book, he says as you put matter into the core of these structures, it goes up through the periodic table and then it gets stuck at iron. and it goes ion, 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 until you get a critical density of, in his words, nucleons and nuclei, an electron cloud in that particular part of the book. And then it suddenly shoots off. Maybe we'll have a look at that page from the book. It suddenly shoots off into nuclei that are in the up to 4,000 AMU, like element nuclei that do not exist in our near universe. You can be synthesizing in this process. Of course, they're probably fantastically unstable when they come out of the condensate. But the argument that I'm making right now is that we know from the claims of the awarded patent Systems and Methods of Generating Coherent Matter Waves of Lockheed Martin that you can cohere matter at any temperature. You just need it to be the same kind of matter, let's say an electron, a proton, a sodium-23 atom, a aluminium-27, a phosphorus-31, and you need it to be at exactly the same phase and energy, and you can manipulate the phase and energy using the Aharonov-Bohm effect. That is why, I mean, you need at the same phase and energy to get a normal Bose-Einstein condensate, and the way that that was originally achieved was to lower the temperature down to basically nearly absolute zero on a substrate, and then everything becomes in phase. And that's the easiest way to get everything at the same phase and at the same temperature, which means that the matter wave description of the matter, the de Broglie wavelength, ends up at the same wavelength, and so they can cohere. The AB effect, the Aharonov-Bohm effect, allows this to occur, and the AB effect is a feature of the fractal toroidal structure at the phase singularities. And so it itself, and that's according to Afanasyev and Dubovik, and they both worked at Dubna, the nuclear physics city in Russia, and it was 1998, I think, the paper. I've referred to it many times. You can go and look at my, let's say, Strasbourg presentation. I give the link in that. And so if you can make coherent matter at any temperature with the Aharonov-Bohm effect, then the overall coherence capability of these structures is effectively able to account for, as it's powering up and keeping its virial stability, is able to account for any energy that's released in the internal contents of the matter. Now, as you keep piling matter in there and it's cohering, you are then moving through the threshold of what will be reborn in the electronuclear regeneration part of the process. So electronuclear collapse is the collapse of matter into this coherent condensate of increasing density, which, because it's a coherent condensate, can maintain its virial stability all the time the fields are there. But when the fields die down, the pressure, the AB effect maintaining coherence fails, and the matter is then re-ejected and spews out, as observed by us, many other authors, and Takaaki Matsumoto. And as I say, it may not be the same elements that go in. And Ken Shoulders is very clear about this, is it's so fantastically efficient at transmuting elements in this process with what he called exotic vacuum objects, that it might be transmuting it to one element and then back to another. And you can imagine that if something becomes unstable and then another one eats it, it's going to then maybe eat other elements, and the overall electron nucleus nuclei macro cluster that's in the core and its level of coherence and its level of density predicates a particular elemental spread coming out. Now, you've seen this in our, for instance, data from the cavitation of on a Mars of vibrator plates, where in the center you have diamond, kind of nitrogen like crystal, and then around that you have double carbon, which was magnesium, and around that you have this kind of like vortex galaxy structure, which is chromium, which is quad carbon. Okay, And I kind of think about that in this kind of, I struggled with what was going on with that for a while, but it might be that a factor of how the coherence fails over a period of time, or it might be that the higher matter wave, or the matter waves arrange themselves in that kind of arrangement. So you get carbon in the core, but when it spins out, carbon spews out first, and the other things are carried with it, and you get the kind of observations that we see. So essentially, protons, I constantly have this phrase in my mind, this warning from Dr. Roy Shinamaza saying, there is this hidden group that do not want people to know about the properties of atomic hydrogen. And atomic hydrogen is protons. And the property that I think is most important is it has this high spin and that it can be aligned. The second one, I believe, is that it is able to reassemble the relic neutrino condensate. And I talked about that in my presentation at Tesla Tech. And those, I think, together are probably the two most important aspects of the proton, atomic hydrogen. And if you saw my presentation from Taiwan just before Christmas, I talked about the fact that in the case of George Eagley's proven now over unity electrical generator, it does not work when there are no protons in play. So I think protons are absolutely critical, and I think it's part of the overall process that's going on. You see, essentially, most of what was formerly called low energy nuclear reactions, most of what coherent energy transformations are HHO, and most of the rest of them are hydrogen catalyzed processes. So I think the proton is absolutely critical. It could be a deuteron or triton, triton being slightly better. Deuteron you can avoid to a degree forming of tritium, but why not just use protons? So to do that again, fractal magnetohydrodynamics or fractal toroidal moment, matter condensation, is kind of non-thermal in the way that you don't see the temperature coming out of the process whilst it's occurring. It's kind of like in there and confined, and it's in the whole kind of coherent center. It's not non-thermal in the kind of like active state. Spinline protons enhance gravitational collapse of coherent matter wavelets. As the matter is condensed by the Aharonov-Bohm effect, coherence into matter wave condensate, there is no typical pressure increase that you would see from Boyle's law and the ideal gas law. High matter densities can be achieved because you're just piling matter into a coherent condensate, and it might be, and I'll do another addendum presentation to this when I've done this at some other point, but I did this thing called Magic Incarnate. Hold on, I've got a video going on in the background here. Let me just deal with this. Where's that going? Give me a sec. This is tedious. Okay. I did this presentation called Magic Incarnate, where I looked at some Hutchison samples, and on there was this bridge, like a solar prominence, and in the middle came down synthesized elements, and it went away and flowed away. In the other part, there was like a black hole vortex, and all around the system, there were these irregular arrays of synthesized spots of elements where you had one element in the inside and then a different element on the outside. And it was like a regular nodes of an interfering field pattern. But in where this kind of like black hole vortex hole was, there was a platform off to one side. And like I say, I'll probably refer back to this in a separate presentation. But there were like magnesium, silicon, carbon, magnesium, but they were in overlapping wave interference patterns. And I kind of imagine that inside this structure, inside the core, there are these structures in there which are self-similar, which are these wavelets. And this is why you see, and we'll look at this again, these toroids in the center of the iron-rich crenellated sphere. And in that toroid, it's got little regular spaced white spots all over it, which are titanium. And so that is what I'm talking about when you've got these wavelets, these coherent matter waves, but the wavelets are interfering and they have therefore a different energy density at different points. And so when it comes out, you get a spread spectrum of elements synthesized. It's really freaking magic. Okay. So the original reaction pathway that I proposed for Huang reactor here, Benjamin Huang et al.'s reactor, was a response that I gave on the 14th of June 2021 to an 11th of June 2021 presentation that he gave in I think Shanghai in China, in ICCF 23, I think it was. But I said that in my view, because most of the fuel effectively was oxygen and hydrogen, the most abundant hydrogen isotope was protons, or protium, and the most abundant oxygen is 16 oxygen. So I suggested that the first reaction that would occur would be this hydrogen and oxygen going to oxygen 17, yielding 3.36 megaelectron volts. Now the problem is for many people that this has a neutrino involved, and of course I was actually calculating this, and this is my slide from my presentation in 2021, and of course I had slightly miswritten reactions down here, but here we go. We've got a neutrino on the left, a proton, and oxygen 16 forms oxygen 17, but the full reaction up here is the proton and the electron plus an antineutrino combined with the 16 oxygen to go to 17 oxygen. Now, normally when you make a neutron from this left part of the reaction, the leftmost part of the reaction, the proton, electron, and antineutrino, you have to give that 782 kiloelectron volts of energy to make that neutron. However, Parkhomov theory is suggesting that relic neutrinos or technologically produced ultra-low energy neutrinos have a wavelength that's in the microns to millimeters, allowing it to interact with trillions of atoms simultaneously. So you can actually get this matter collapse, this electronucleus macrocluster collapsing simultaneously to 17 oxygen, and the net yield is 3.35897 megaelectron volts. And because that is positive, it will proceed. So you do not need to make the neutron first. This just proceeds. So it's kind of catalyzed by the proton, but also catalyzed by a flux of relic neutrinos. And I argue that the relic neutrino condensates have a toroidal moment. The relic neutrinos themselves have an anapole moment. They are both low energy, and they can be influenced by the toroidal moment of the wheel within a wheel structure. Okay, so neutrinos and antineutrinos are pulled in. In the case of antineutrinos, they help build matter, and in the case of neutrinos, they help disassemble matter. So the antineutrinos is very much associated with the yin side of the yin-yang process, and the neutrinos are, the relic neutrinos and clusters thereof, are associated with the yang side, the disassembly of matter. Okay, so he observed a lot more oxygen and oxidization of the copper pipes, these tens of meters of copper pipes in the heat exchanger. And so that was the explanation for the oxygen. But of course, I couldn't focus on the oxygen in my analysis because it's a process that involves cavitation of water. It was the carbon that was interesting. Anyway, in my presentation at in Taiwan, I talked about Egely's hypothesis, and Egely's hypothesis was what I've just discussed here, the synthesis of a neutron from this process here, which is essentially the left side you've got up here, and having to put this 780 keV, it's actually 782 keV, in to synthesize the neutron. I do not think this is necessary, but at the end of the day, it doesn't matter to what I'm talking about today. There is some means by which you are doing a yin process. That is a condensation of matter into heavier matter and releasing energy. Electron capture arguably can do it differently, and this is the one that I think was proposed by the editors of the paper that I did with Binger and Huang. There's also a beta plus decay of a proton. The problem with the beta plus decay of a proton, it produces a neutrino and a positron, and of course the positron will annihilate with an electron, and it leaves you with a lack of electrons in your process. You have to take them from the environment. That's okay. It might end up by producing an anode. And it's something similar to what Matsumoto proposes, where the electrons polarize the proton, leading to this kind of process going on up here, and it forms this thing called an iton. But anyway, and I also just dropped this thing in here that, like, if we could create this intense magnetic field at the core, then you could disrupt the proton if you gave it some energy, and we know there's a lot of energy flying around in there, producing a positron and a neutrino and the neutron. So it's fairly similar, but I don't think any of this is really necessary to dwell on too much. The key reaction that I was focused on was, how is he getting the carbon? Well, from this reaction, I'd already established that the most likely reaction to come out of this initially was the production of oxygen-17. Oxygen-17, as I've discussed before, is not only paramagnetic, it is a spin nuclei, so it's more desirable to get locked into the core of the coherent energy transformation process. So the very first most likely reaction, once you've synthesized oxygen-17 in a coherent matter process. Now, why am I saying coherent, and why am I trying to focus on that? Because if we are going to create coherent matter, what is the most likely equation here that is going to create coherent matter? Is it oxygen-17 and oxygen-18? Is it oxygen-16 and oxygen-18? Is it oxygen-16 and oxygen-17? No, because these are different isotopes. I'm not saying you can't get this through matter wave or wavelet interference. What I'm saying is it's less likely that these things can be cohered because they're not the same original matter. Do you understand what I'm saying? The core of the systems and methods for generating coherent matter wave, patent by Lockheed Martin, focuses on the isotope or electron, for instance, being the exact same initial matter. Okay? So, the only oxygen-16, 17, no. Oxygen-16, 18, no. Oxygen-17, 18, no. So there's only two reactions here that are most likely to occur in a coherent energy transformation process, and that is this one, oxygen-17 and oxygen-17. And that produces 0.99, but in a process that is trying to squeeze things into the smallest box possible to yield the most energy from lowering the distortion of the physical vacuum, the first reaction that is most likely to occur, in my view, as it was in 2021, is the fusion of oxygen-17 and oxygen-17. That yields carbon-12, which was observed by Binger and Huang, and neon-22 in isolation, without neon-21 or 20, by Binger and Huang. So the most likely reaction to occur in a coherent energy transformation process produces the carbon-12 observed, and also produces the neon-22 observed, which does not also have neon-21 and neon-20. Okay? I also predicted in 2022 that this paper, 2014, talking about the phase relationship in axial hypertoroidal moment. Hypertoroidal moment is the Western term for what I call fractal toroidal moment. In Russia, they call it supertoroidal moment. I call it fractal toroidal moment because of the way it's arranged. Now, if you change your phase angle here, when you get it up to 90 degrees here, aspect ratio, you get these apple shapes. These oblate spheroids, which are the same kind of structure that you get from a Kerr-Newman black hole, which I think is a related kind of thing. And depending on the field, you get a vortex one way or a vortex the other way. Okay, and when you do the yin-yang potential here with these determined field distances, you have the ability over the scale of what I'm just about to show you to split water, which is necessary for producing the atomic hydrogen and the oxygen. Okay, so I predicted these things in 2022. I showed this slide again to Binjuan Huang in late December 2023. He gave me a sample for the first time from his reactors on December the 29th, 2023. And in March, I imaged this on the 28th of March, 2024. And it's an exact and perfect yin-yang, and both of them have a yang-yin and a yin-yang in respectively. Okay? So this, in my view, is this. This is caused theoretically by a hypertoroidal moment. This is in a major Physics Review B peer-reviewed paper from 2014 talking about how the magnetic field would present itself. And this is exactly in my view, the physical manifestation of that. First time it was ever observed in any form of research. Okay? As a physical manifestation. You can see that these are very large. So this is much more than 10 microns. This is around about 20 microns over the course of this structure. Now, the very, very interesting thing that came out of this was, weirdly, there is a high concentration of phosphorus on the outside. Now, this core structure here was strong in iron, you can see. So you can see the phosphorus here is all of these bits, the outside of these structures. The copper is in the background. The chlorine has a couple of spots here. There's one spot there and another spot down here. But the iron is in this structure here. So this is more like a core structure, and this is the outside of this structure. Now, if we dig into the core of one of these structures by looking into a broken one, we have a broken one up here, and we're looking into the core of this structure, and we look at 209 here, we see 209, and other than having 21% carbon and oxygen, like I say, we cannot consider oxygen to be synthesized because we are having water in the system. But because there's no carbon in the system, we can certainly consider the carbon as being an interesting product, and we know from this that carbon gets synthesized in these processes where it is not present before, and we've seen it in other systems. I mean, Svyatomenko saw it, Mikhail Solin saw it in 1992. This is not new, but having the level of detailed understanding is taking things forward. Okay, so carbon and oxygen. Now you can see magnesium here, which is double carbon, and aluminium is a byproduct of carbon and oxygen fusing and producing aluminium and a proton. Silicon is a direct fusion of carbon and oxygen. Look, we've got 5.47% in the core of silicon. And then phosphorus in the core is 3.58%. So it would appear that silicon and phosphorus are formed in the core. You can also see a lesser extent of sulfur here, which is the fusion of double oxygen. Some chlorine, which we also saw on the outside. Some potassium, calcium, iron. What are all of these elements? These elements, my friends, are the elements that are denuded in soil when you have crops. These are the critical elements: phosphorus, potassium, sulfur, calcium, magnesium, really critical elements for good soil health. Even iron to a degree. Okay, and these peaks are not small, they're strong. So this is 0.209 from the core here. Here we have 0.210. And again, what have we got? We've got 3.18 of silicon, 3.24 of phosphorus here. Chlorine's a little bit higher here. Up here we've got carbon has dropped a bit and oxygen is higher here. Okay, but again, we have oxygen in our starting system. We cannot be certain that it is produced, but we don't have carbon. Okay, and we don't have these kind of elements. And the elements are not on the pipe. This is basically the pipe. You can look at the, I will show you the whole PDF, but the pipe is basically copper and oxygen, and it has some of the elements to a small degree that you can imagine are synthesized in the structure and are synthesized in similar systems, but it's kind of like the spilled guts in my view. Okay, so when we look at the potential reactions between just oxygen isotopes, and remember what we're doing here, we're doing coherent energy transformations. Coherent energy transformations. Yes, you can have interactions of elements in wavelet interference and wave interference in the matter waves, but ideally, according to the Lockheed Martin patent, awarded patent, you need the same matter at the same energy and in phase, which the Aharonov-Bohm effect allows to create. So let's look at the reactions you have with oxygen here. Okay, and I've done these all without neutrinos to avoid any complications. You can go and have a look at the reaction here and switch the neutrinos back on if you like, on Brian's fantastic iteration of the Parkhomov reaction calculator. And as we go down here, we can see there's this very, very high energy reaction here with oxygen 17 and oxygen 17 producing silicon and helium-4, of course. Now we see silicon, and also Binder and Huang has observed helium-4. Okay, 16 and 18 not good for coherent matter wave. 16, 17 not good. 16 and 16, what do we see? We see helium-4 and the most abundant isotope of silicon. What are the chances? What are the chances? What do you have a lot of in the Earth? You have a lot of silicon. Okay, second most abundant element in the Earth's crust. Where do you see helium? You see it coming out of the bowels of the Earth. Could oxygen 16 and oxygen 16 producing helium and silicon 28 from a fusion fission process, a coherent matter wave process? Okay, this is not a stepwise process. I'll come on to that later. This is oxygen 16 that already exists synthesizing directly silicon and helium-4. Well, we saw silicon in the cores. We saw silicon in the cores. Here we go. That is physically the core of this broken structure, and we see silicon in that core. We see silicon, here we go, 2.68, 3.18% by mass. Okay. So we see silicon. Now the next one, which is a coherent matter wave, is 17 and 17, but that produces tritium. The process tends not to like to produce radioactive material. It does produce tritium if you're starting with protons, okay? But this is an unlikely reaction, okay? And we're not starting with majority 17 oxygen. We're starting with the majority of 16 oxygen. So the next one down here, oh my God, boom! The second most likely reaction with the most abundant oxygen isotope in natural water produces a proton and a phosphorus 31. A proton and a phosphorus 31. And you know what? That for me makes it the #1 reaction. And I'll tell you why in a little while. But what happens is that these two products share this energy. They share this energy of 7.68 million electron volts. And if you want a proton, this is why I'm talking about this. If you want a proton to do this reaction here, into here, just kinetically going in, the Coulomb barrier between this is about 2.7 million electron volts. So it will just go in, it'll build the neutron it needs, and it'll become oxygen 17 from literally particle collisions. Okay? But the other way you can think about it is that you are inserting a proton in the overall system. So you can imagine coherent matter waves going around of oxygen 16, and in the core you've got coherent matter waves of protons, and then the oxygen 16s, their matter waves interfere such that they produce this phosphorus 31, which is getting, majority of it's getting ejected. Some of it we see still in the core, but there's a proton which, because of its nuclear spin, is immediately pulled in, cohered, and adds its energy to the core of the system. So it's a high energy product. The high energy product potentially can lead to causing these secondary reactions. Okay, so let's go. The next thing that I predicted was that there would be iron-rich crenellated microspheres, and in a sample of detritus that came from his reactor, they were in abundance. And you know I've seen these in many different things. Here it is, and my argument is that they are hollow. And sure enough, we saw that it was hollow, and we start to see these toroidal-like structures in here, and we saw a broken one, and in that broken one, you see these toroidal-like donut-shaped sections, and we know that these magnetohydrodynamic vortex things, they come in and they go into the core, and you see these red little nodules over this. What is it? Well, that core there, and I've sampled it here. So I'm sampling this point here. Overall, this is rich in titanium. What is titanium? It's the fusion of CO2. It's the fusion of CO2. There's other ways you can get there. We can look at that in a second. But it's the fusion of CO2. Again, you can see silicon here. Now, there's the titanium, 22.92%. We've seen the same kind of ratio in Henk-Uren's Vega experiment, but we observe titanium in high concentration here. So carbon, which we can say looks like it's been synthesized. We've got nitrogen, could be synthesized. There will be a partial pressure of it in the deionized water. Not so, you can have the CNO process going on. It's a standard nuclear process going on in the sun. Using the alpha particles, we know it would appear, we observe helium in the products from the Benjamin reactor. I argue that they're produced in the core, and if they're energetically produced in the core, like I just showed you, to produce the silicon that you observe, and you can't observe helium or hydrogen by EDS, then it could then form this, carbon 12 to oxygen immediately, transformation. Okay, but titanium is fusion of carbon and 2 oxygens, okay, in the ratio CO2. Okay, so we see titanium. So let's look at this overall process. The first most likely reaction after you've synthesized oxygen 17 is a coherent energy transformation reaction that produces sulfur 34. It's massively more energetic, which means it does the most reduction in the distortion of the physical vacuum. The most reduction in the distortion of the physical vacuum. Therefore, it's most likely to occur. Okay? This is 16 and 18, not likely to happen so much in a coherent energy transformation process. 16 and 17, not so likely to occur in a coherent energy transformation. 16 and 16, well, that is. That is. So rather than the reaction that produces a proton and sulfur and phosphorus 31, we have 16 and 16 producing sulfur 32. And we observe sulfur in the cores of these reactors. It's less energetic, so it's kind of like less likely than the other than some reactions. But anyway, this is a coherent energy transformation process. We observe sulfur. We've observed it in several different experiments. So the number one output when you have oxygen 17 involved, which we know we do, and oxygen 17 preferentially wants to be in the core because not only is it paramagnetic, it's also a spin nucleus. The second step is this, sulfur 34. So the single most likely product to come out of oxygen 17 fusion is sulfur 34. Sulfur 33, not so likely to be there. Sulfur 32 and 34 is not a coherent energy transformation optimized process, but sulfur 34, this is the number one product. And you know what? It produces carbon 12 and iron 56. And this is what I proposed in my O'Day HHO presentation as a reconsideration of the Sundaresan and Bokris work, and I'll actually click on that now. We will see it is here. I did this in O'Day HHO, and I said, based on the understanding shared in this presentation, I predict that iron in the iron-rich crenellated spheres made in the magnetic core of fractal toroidal structures in Ultra and Vega, and by extension in natural ball lightning, will be overabundant in iron 56. And I think this is the type of iron that was in the George Ossawa steel. But basically, it's this paper here, where they observed anomalous reactions during arcing between carbon rods in water. And it's here, George Miley is discussing this as being very, very interesting. And it's a brilliant, brilliant work. But they assumed a reaction which relies on 2 carbon 12 and oxygen 18 being present, going to iron 56 and 2 4 helium. They did not look for the 4 helium, but this reaction produces the same yield of energy that they observed in raising the temperature as the reaction that I proposed. And if you go to actually here, have I got the actual reaction? I think I might have to look in the presentation here. I actually proposed, actually no, I actually have it. I can pull it up. I actually have it somewhere. Yeah. I can go here, and I went here. Okay. Okay. Yeah. In fact, I've actually got it in the presentation. So this is from O'Day HHO. So based on the finding from Benjamin Huang, my prediction, and then it being verified, the production of 12 carbon and 22 neon from the fusing and fissioning of 2 17 oxygens. If you take 4 17 oxygens, 2 of each make sulfur 34, you get 12 carbon and iron 56, and it's basically the same amount of energy that you get from their reaction. And so I would suggest that if they actually looked at the morphology of the iron that they would be creating in their experiment, they would find that the iron would have been an iron-rich crenellated microsphere, like this one from natural ball lightning, this one from the ultra replication by Alan Goldwater, and this one in the Henk urine Vega experiment. Okay, and I think that if we look at these iron concentration in here, I think they will be rich in an overabundance of iron 56, which is already the most abundant element isotope of iron. Okay, so back to the main presentation. So just to go through it again, we've explained how we get to oxygen 17. The most likely product from this in a coherent energy transformation process is sulfur 34. That is observed, or sulfur is certainly observed. It's observed in natural ball lightning. It's observed in Amasa gas on the 10 yen coin, and so forth. The first most likely reaction to occur, and the only one that you've got on the list here that's a coherent energy transformation, produces iron 56, the most abundant isotope of iron, and carbon 12, the most abundant isotope of carbon. And I believe that this is the effectively 4 17 oxygens fusing, all simultaneously actually. I think it's just 4 coming together. You never see the sulfur 34, and it just goes straight to carbon 12 and iron 56. Carbon is in the core and gets spewed out. And iron 56 can produce part of the iron-rich crenellated microsphere. Okay. Now, what happens also is you can have side reactions, which are not specifically coherent matter wave interactions, where you get, for instance, neon 21 and sulfur 34 directly producing iron 56. And you can see that it's basically the same thing. It's basically the same thing, just coming at it from a different angle. Because when you form the carbon, when you form the, where is it, the neon 22, you lost a carbon. So when you come down here and you make it, it's basically the same reaction, just looking at it from a different angle. So I show the Sundaresan and Bokris here. Okay. Now to get the titanium here, There's a couple of pathways you can get there, either from carbon-12 and sulfur-34 to titanium-46, or 47, you got oxygen-17, and here phosphorus-31 gives you titanium-48. This is the most abundant isotope of titanium. Okay? So we have a process that produces phosphorus. We can see it's actually producing phosphorus. This is not guesswork. The outside has phosphorus and the core has phosphorus. It's rich on the outside. We're going to look at the more data on that. And you can see that it's like 7, 8, 9% phosphorus on that entire large structure on the outside and on the structures of the sub-tores in there. And the phosphorus, in my view, is required 2 oxygen-16, the most abundant isotope in oxygen in a coherent energy transformation process, produces protons and phosphorus. The protons catalyze the proton coherent energy transformation process potentially, and the phosphorus is energetic, and the phosphorus can interact with the oxygen-16 here, or the oxygen-17 here, to produce isotopes of titanium as observed. Now, I say it could be CO2. It could be CO2. But there we go. And all these things are observed in Huang. So I now want to take a look at this from a completely different viewpoint. I want to focus on where I started out about making coherent energy transformations right from the core. We know we can get aluminium-27 and aluminium-27 to fuse to iron-54. I believe that kind of reaction was the kind of reaction that was going on in Castle Bravo with the nearly 50% of aluminium that made up that bomb. And it's verified, in my view, by the crenellated microspherules that were captured by Avi Loeb in his so-called alien downing kind of thing. Right? Okay. So coherent energy transformations. I think one of the most important pieces of data is this, which is from the 2003 patent of the Ukrainian SV Adavenko. 20,000 experiments, I think it was, or 10,000 experiments in a row, using every metal in the periodic table, 300 joule discharges into it, produced from those pure metals, all of the elements in the periodic table. But this is the single photo of an SEM that he decided to include in his 2003 patent. And what you're seeing around the outside here is the 99.999% pure copper accretion disk. This was a 99.999% pure copper target, and it produced this predominantly, that is 93% by weight, iron with admixtures of silicon and, of course, some copper isotopes, okay, in the background, okay? So mostly iron and silicon. And he said in a 2005 interview in a Ukrainian newspaper that he thought, having done all this work, that the reaction occurred in this hollow area by way of dark matter. And in his own work, he says that in this area where this nuclear reaction occurs, he says there's an electronucleus nucleon macrocluster. That is in the hollow zone, and the nuclear reactions occur via dark matter interactions. Okay, now dark matter, relic neutrinos, relic neutrino condensates. You know, one name given in the past to a relic neutrino condensate is an axion, which is a candidate for dark matter. Anyway, there we go. There's actually a paper out, I think even just a few days ago, that says that neutrinos can interact with dark matter, and it might change all of physics. So you can go and have a look at that. Maybe I'll post the link to that in the blog. Okay, but I think we know that. So effectively, following fractal magnetotoroidal moment containment field collapse, the newly synthesized matter's isotopic composition is determined by the decoherence of the local coherent matter density and wavelet interference, according to my view. So I'm now going to run over what I'm considering is I'm going to do it one way as a stepwise process, and then I'm going to, like I did, for instance, for the production of iron in Cinderace and Bockris, and a couple of times before, I'm going to consider a full-on electronuclear collapse, a gravitational collapse of a whole bunch of coherent matter. So the first way to look at this is you start with your proton and you make a deuteron. Now, one of these protons could be the energetic proton produced from the coherent energy transformation process between oxygen-16 and oxygen-16, synthesizing a high-energy proton and a high-energy phosphorus-31. Regardless, this is the first step in the process, and if we have one of these as high energy, then we can trigger this process, and then the 1.44 MeV is sufficient to trigger the process in many other protons in the matter wave condensate. So it's kind of like, it's a cascade process. Once you've got our deuterons, you can take 2 deuterons and make helium-4. Now, this is a reaction where normal kinetic nuclear scientists go, you're never going to see helium-4 except in a very vanishingly small amount of processes. And the energy will, how do you get rid of the energy? It's a gamma wave. Well, the gamma wave will be emitted in ordinary processes, but it will go into that energy will go into the coherent matter. And so it will not escape the system. Okay? Then we take a deuteron and we fuse it with helium-4 and we get lithium-6. Not a lot of energy in this. Okay? Remember, what we're trying to produce is the carbon that we see in all of these systems. All of these systems. 2 lithium-6. So here we go. Lithium-6, they fuse together to make carbon-12. 28.18 million electron volts. So what have we got here? We've got a whole bunch of these, 1.44 million electron volts. A bunch of these, 23.85. We've got 2 of these, 1.47, and we have one reaction of this. Okay? I don't know why I got that there. Oh, I've got a whole bunch of these in a row. Okay, I'll get rid of those. They're unnecessary slides. I must have got trigger happy with copying slide. Okay. Okay. So the combined reaction here is you start off with 2 protons and 1 electron goes to deuteron plus an antineutrino. This is one way of looking at it. Okay. But whatever, it produces 1.44195 million electron volts. This is reaction 1. 2 deuterons to 4 helium, 23.8472. Deuteron plus 4 helium, 6 lithium, 1.4708. 6 lithium, 6 lithium. So if we add all these up, we have 6 times R1, 2 times R2 plus R3, R2 plus R3, plus R4 gives you 87.468 million electron volts. That is how much energy you get from fusing all of these stepwise processes. But I don't think it necessarily needs to be stepwise. What it could be is the coherent energy transformation process would just be with electronuclear collapse of a condensate of protons. So effectively, you could look at it like this. Let's double it up for the sake of argument, so we've got 2 products at the end. You double up, so we would get 24 protons, 24 electrons, leading to 12 protons and 12 neutrons, and 12 electrons. This results in a pair of 12 carbon nuclei, and an energy of twice this, of 174.936 MeV, and this gets shared between the products. So effectively, you've got 24 atomic hydrogen. Atomic hydrogen is a proton and an electron. They all come together in the coherent condensate, and they electronuclear collapse into 2 carbon-12s, and they come away with the combined yield energy of 174.936 million electron volts. 174, roughly, let's call it 175. 175 is about the energy that you get from fissioning of a uranium-235 atom into two products. Now, the products are toxic. Carbon's not so toxic. It might be as carbon monoxide, but carbon isn't so toxic. And with the other energy that you get from gamma rays and prompt neutrons and some beta particles from the decayed products, ultimately in a normal fusion reactor, that kind of work out that approximately a fission reaction ultimately yields you about 200 million electron volts. So it's still comparable with what we've just calculated here from electronuclear collapse of 12 or 24 protons, or atomic hydrogens rather, to give us 212 carbon. Now, I'll just reiterate again that potentially the oxygen 16 and oxygen 16 here producing the proton and the phosphorus 31 could be the activation energy that is required to do the rest of the process. Okay, so just to go over that again. Initiation energy comes from R0, which is this one, R0. The actual production of the phosphorus from coherent energy transformation of oxygen 16 inside the core, and the Aharonov bomb effect forces coherence. So despite the fact that all of this energy is released, the energy is imparted from that proton into the condensate and is shared instantaneously by everything, and the AB effect enforces coherence in the core. This leads to production of one atom of carbon via coherent energy transformations, yielding 87.468 MeV. Now, I then went to Binchuan Huang and I said, like, how many liters of water did you have in your best producing COP reactor? And I think it was 4.26, the COP. I've just put here, for sake of argument, over 4. He told me he had 60 liters of water, and it was kept in a tank by cooling the output from the heat generator to maintain the tank storage at 50 degrees centigrade. Okay, but for sake of argument, what I've done is I've said, if we are producing 87.468 million electron volts from the production of one carbon, forgetting the actual initiation energy of producing the initial proton from production of a proton and 31 phosphorus from 216 oxygen. If we just focus on the yield from taking 12 protons, 12 electrons, and doing the CRT, coherent energy transformation process, and yielding 87.468 million electron volts, how much carbon do we need to synthesize to raise that 60 liters of water by 80 degrees C? And it turns out that if we take the graphite form of carbon, which is less dense than diamond, and we know we've produced diamond in these search processes, it needs to be approximately 1.264 times 10 to the minus centimeter cubed. Okay, so not a very large amount. What does that constitute? We need to produce a cube of carbon with a side length of 0.0233 centimeters, or 233 micrometers. Boom! We can raise 60 liters of water from standard temperature and pressure 20 degrees C to the temperature of boiling water, like it's on the threshold, it's 100 degrees C. It's suitable for making a good old cuppa of the tea, making our lovely English brew. If we can do that, then we need a cube, or to raise that 60 liters of water by 80 degrees centigrade, we need to synthesize enough carbon to fill a graphite cube with a side length of 233 micrometers. Okay. You can have coffee too, and you need less temperature, actually. It's better for coffee, to be honest, because you shouldn't burn coffee, and so you should keep the water at about 90 to 95. Anyway, it's better for coffee. So I thought, if we want a cube this big, how much are we synthesizing in these structures? So here we go. These are two structures from the analysis of the DHX2 core, the collapsed pipe. So this is a bare core where the outside broke up and it didn't spew out. And we can see from this scale that it's approximately a 20 by 20 micron cylinder. Okay, we can also look here, we can see that it has 50, I actually turned the carbon off in this one. It's got oxygen, sodium here, potassium, we have our phosphorus and silicon here, not so high concentration. I think I turned the carbon off in this one. But this is one core. The second one here is directly associated with a broken structure. And again, this is a 10 micron scale, so it's approximately 20 microns by 20 microns. You can see it little bit more unraveled than this one, and I think it's because it had to work its way out of here. And we can see the carbon here is about 52.58% by mass normalization, and by atoms it's 67.03%. So the carbon synthesized here or present in this core is 67.03%. Again, I cannot talk about the oxygen because we are starting with water. We cannot consider that. But because we don't have any carbon in the system, we can consider the carbon to be synthesized, and we know carbon gets synthesized by this process by, for instance, Matsumoto, carbon here, and other researchers in this field. Okay, so using these numbers, a cylindrical core of 20 micrometers wide by 20 microns tall has a volume of 6.2832 times 10 to the minus 9 centimeters cubed. Therefore, we need 2,012 of these if pure carbon, or around 4,000 of these if 50% carbon at density of graphite. Right, so I am making an assumption that the density of this thing is about the density of graphite. I'm also assuming that it is just 50%. 50%, not 67.03% atoms, but 50%, okay? And therefore we need approximately 4,000 of these little cores. Now what I did is I went to a different part of the video flux capacitor. Flux capacitor. This is when I, for the first time, revealed the analysis that I did in March 2024 of the cores of some of the reactors of Binju and Huang. And in there you can see in the video recording of the microscope session that the frame size of the area under inspection that I'm just about to show you is 1 millimeter by 0.75 millimeter. What am I referring to? I'm referring to this, okay? And this is 1 times 0.7, so 1 millimeter across here and 0.75 of a millimeter. And you can see a whole bunch of N-level tori, N-1 level tori, and N-2 level tori, okay? You can actually see some carbon spewing out of N-2 tori and some carbon spewing out of N-level tori, sorry, N-1 tori and spewing out of some N tori. What I did is I did some contrast adjustment on here, and then I put it into a machine vision system, and I found out that effectively it calculated that there are about 82 large clusters, and these are either flat on, i.e. the donut is sat down on the, like this one, and this one, and this one, and this one. They're kind of like sat down on the copper oxide, or they're on their side, like this one, and this one's on its side, or they're broken. There's some fragmented ones. So there's like a fragment one here and a whole one here, okay? It also found 633 smaller cluster parts, okay? Now, if you assume that 2 of the N-1 clusters make up a former N-level cluster, this would represent somewhere between 200 and 400 large clusters in an area of 0.75 millimeter. I wanted to be really, really conservative. For the sake of conservative calculations, let's approximate the source of the parts to be from 100 clusters per square millimeter. So the machine vision system already determined 82 large clusters. And if you just count down on the bottom left-hand corner here, I'm just visually 1, 2, 3, 4, 5, maybe 6, 7, 8, 9, 10, 11, 12. There's 12 in that little area there, maybe 13, 14 here, 15 here, maybe 15 in this little area here. So I think I'm being really rather conservative to suggest that in a 1 millimeter area, which is a full 25%, well, 33% larger than this area, there will only be 100 large clusters responsible for all of these impact strikes. If you do the calculation, we need 4,000 of these structures. So assuming 100%, that should be per, that should be per millimeter squared. I will change that now. Okay. Fix my slide. Assuming 100 per millimeter squared, we need a pipe surface area of 40 millimeters squared. So for a 10 millimeter outer diameter pipe, length of 1.23 millimeters is needed. If the density was 1/10 of that, i.e. just 10 per square millimeter, I need to check these calculations. I might have got it wrong, or Grok might have got it wrong, because I asked the wrong question. Maybe I made a mistake here. But anyway, even if there were only 10, if there was only 10 large structures in an area 33% bigger than you see here, 33% bigger than you see here, if there were only 10 of these structures, and internally these structures, they were producing carbon, and I'm saying it's not at the observed density of 67.03%, I'm saying it's only 50% carbon. So just 10 rather than 100, we would only still need a length of pipe 1/2 of an inch long to produce the energy to heat the 60 litres of water by 80 degrees centigrade. I am absolutely certain that given the observation of mass 3 elements, which are tritium and 3 helium, the observation of deuterons, that's heavy hydrogen, and in case of tritium, heavy hydrogen, in the observation of neon-22, the observation of phosphorus 31, the observation of iron, the observation of carbon synthesized, and so on. If you ignore all of the other synthesis and just focused on coherent energy transformation of protons directly through electronuclear collapse into carbon, for every carbon atom producing that 87 point whatever million electron volts, you only need potentially as little as a section of pipe 1.273 millimeters long to heat that water up to by 80 degrees centigrade, those 60 litres of water. Now, I know what you're all asking. You're all asking, how many cups of tea? That's all I want to know. Just how many cups of tea? Well, we'll come on to that. I am considering writing a paper. You'll be pleased to know. I have done I've done a whole bunch of calculations. What do I want to do? Before I go on to that, I'm just going to show you some of the data from the DHX2. I think I've shared this already when I did the what do you call it? Flux capacitor. So here is the PDF. It's a Word document actually. I think I shared it as a PDF. DHX2D. That's the original image that I shared you. These are the elements that are being synthesized. That is the map. Here's another one. We're looking at a little bit of the outside of this lighter thing here. Again, phosphorus is present there and sulfur. This is the outside of one of these smaller substructures. You can see this is 8 microns, so this is probably a 5 micron N-2. But again, the phosphorus peak is huge here, absolutely huge. Okay, that is the most significant element after carbon and oxygen. Again, this is the section. Oh, sorry, what have I done there? This is the one that I showed earlier with these 2 core areas here. And yeah, you can see all of the elements. Okay. So I will share this again. But you can see wherever we're looking, whether in the core, we get these strong peaks of phosphorus, magnesium, you know, potassium, calcium, all these beautiful elements for putting on your crops. Again here, big peak of phosphorus. What are we looking at here? There you go, mass is 3.13%, but the majority of atoms still are carbon, okay? So it's the same story wherever you look here, all of the elements in these structures. Okay. Right. Okay. So I'm just going to show you some of the calculations here. In our stepwise process going through from protons here, protons to deuterons, deuterons to helium, deuteron and helium to lithium-6, and lithium-6 fusing 2 of those to carbon-12. We calculated we are getting 87.5 million electron volts. To twice that would be 174.936 million electron volts, okay? So in this paper that I'm preparing, confirming the energy yield by mass difference, we will calculate the net energy released where 12 hydrogen molecules, so that is 24 protons and 24 electrons, equivalent to 24 atomic hydrogen atoms consisting of 24 protons and 24 electrons, and 12 electrons, antineutrinos, can transform to produce 2 carbon, 12 atoms via 12 instances of an assumed reverse beta decay process. So this proton plus an electron plus an antineutrino goes to a neutron with energy in there, but the energy is provided by other reactions triggering the process, as we talked about earlier, and then it's a cascade. The overall reaction conserves particles appropriately. The 12 conversions consume 12 protons and 12 electrons and 12 antineutrinos to produce 12 neutrons, leaving 12 protons, 12 electrons. These combine with the neutrons to form 2 neutral carbon atoms. Total 12 protons, 12 neutrons, 12 electrons. The net energy released is determined by the mass defect between the initial and final states converted to energy. The antineutrinos will be considered to have negligible rest mass, approximately 0, so they will not contribute to the mass balance. So the atomic mass of proton is 1.007825 units, mass units. Atomic mass of 12 carbon is 12 units exact by definition. The initial mass from 24 protons is this, 24.1878. The final mass is 24. Mass defect for the mass transformation is 0.1871. You convert the energy using this factor, 931.494 MeV over C. And so the energy of the coherent energy transformation process is 175 MeV. How does that compare to what we calculated using the Parkhomov reaction calculations? We calculated that to be, if I can actually get there, where has it gone? There we go. Why is it not letting me show that? There we go. Okay. We calculated it to be 174.936. Okay. I think it's pretty close. I think this may be more accurate. I'm not sure, but I think it's rounded it up, the other reaction calculation. So yeah, almost exactly the same amount. This accounts for the endothermic cost of creating the neutrons embedded in the mass differences and the exothermic nuclear binding in forming the carbon atoms. The result is positive, indicating energy release. So, if you can imagine, we've created those 2 carbon atoms out of the 24 atomic hydrogens in the electron nucleus macrocluster in the core. It's produced that 175 MeV, and that 175 MeV is instantaneously shared between the matter wave condensate. And so it doesn't essentially really change the stability. It doesn't change the pressure particularly, maybe infinitesimally small by changing the de Broglie wavelength of the matter wave condensate. And it's only when the confining field collapse that the electronuclear regeneration occurs, that the energy is effectively released as those atoms become ordinary atoms out of the condensate. So it's like a hot atom, a hot macro atom, or a hot coherent condensate that comes out and splits into trillions and trillions of new atoms, and they give the heat out of the process. Okay. Right, now, here's the calculation for determining the cube length of the produced graphite needed to heat 60 litres of water by 80 degrees C. We wish to determine the volume of graphite that must be produced and the side length of the corresponding cube to release enough energy to raise the temperature of 60 kilograms of water by 80 degrees C, assuming each carbon atom produced releases 87.468 million electron volts of energy. The energy required in joules is this, so you work that out. I will share this so you'll be able to confirm, and I wish you to try and confirm everything I'm saying here. Energy released, energy per carbon atom gives this in joules. So the number of carbon atoms required is this. The mass of carbon here, based on Avogadro's constant, and the molar mass of carbon is this number of mass of carbons, 2.856 times 10 to the minus 5 grams. The volume of graphite is based on graphite's density of 2.26. That's the ideal crystal density of graphite, is this. And that gives us a cube side length of 233 microns. So the final result, required volume, is that leading to the side length of the cube, 233. This is a cube of produced graphite less than 1/4 of a millimeter on each side. Okay, right, next, implications for swimming pools. Now, trust me, I'm gonna come on to the tea. I know everyone's waiting for the tea, but I really like swimming. I went swimming today. I like swimming in hot water. I had the pleasure of doing that for eight and a half years of my life when I was living in India in the sea there. It was like 33 degrees. It was beautiful. But swimming is one of my great joys. And so I thought I'd just do swimming first. And we'll do that. It's very good for you. Swimming. Implications for heating swimming pools. If we were to produce just 1 centimeters cubed of carbon via coherent energy transformation CERT process, how many Olympic-sized swimming pools, Olympic no less, could we heat by 15 degrees? So let's say your ambient temperature is 20 degrees, that's 35 degrees. Oh, that's kind of getting on to jacuzzi temperatures. We like that. But let's say you've got a cold environment, it's 10 degrees, you can still just about swim, okay, in 25 degrees. It gets a little bit frosty in 24, but let's say everyone's got their base water temperature at 10 degrees at least. They're going to be happy swimming in 25 at worst, but ideally we're going to be somewhere between 30, around about 30. The energy released by producing 1 centimeter cubed of graphite, based on 87.468 mega electron volts per carbon atom produced, can be used to heat Olympic-sized swimming pools by 15 degrees. The calculation proceeds as follows. So you've got the graphite density there again, you've got the molar density there again, you've got the number of atoms, the Avogadro's constant there, so you need to know that. The energy released per E atom produced is that. That's similar to what we showed above. The total energy released is this. Now, the mass of one Olympic-sized swimming pool, 50 meters by 25 meters by 2 meters is 2,500 meters cubed. Density of water is 1,000 kilograms per meter cubed. This is 2.5 times 10 to the 6 kilograms. Energy required to heat the pool by 15 degrees based on the specific heat capacity of water. You can see this is all brewing up to our final T determination. 4,184 joules per kilogram degree centigrade. Temperature change delta T 15 degrees centigrade. So the Q pool is the mass of the pool times the specific heat capacity of water times the delta we want to achieve, and that is 1.59 times 10 to the 11 joules. Whew, that's a lot of joules. Right, number of Olympic-sized pools that can be heated by 15 degrees is 10.13. 10 Olympic-sized swimming pools can be heated by the production of carbon using coherent energy transformation processes of a side length of 1 by 1 by 1 centimeters. 1 centimeter cube of carbon. Waste product. Waste product. Carbon. Oh, terrible waste product. That evil carbon thing. Even imagine the carbon credits that you're going to have to buy to account for that 1 centimeter cubed of carbon. You might have to use something really fungible, like a billionth of a crypto. Anyway, thus the energy released from producing 1 centimeters cubed of graphite could raise the temperature of approximately 10 Olympic-sized swimming pools by 15 degrees centigrade. Right, this is what you've all been waiting for. Implications for brewing tea. Determining the number of 250 milliliter cups of tea that can be heated by 80 degrees C. Now, you can see why I chose 80 degrees C for my calculations for Binge-Ren Huang's 60-liter reactor. It's taking it from standard temperature and pressure, 20 degrees C, up to a good brewing temperature of 100 degrees C, non-vaporizing. This is 100 degrees C, perfect for brewing the proper tea, which is black tea, right? Preferably English breakfast tea, from the energy released by producing 1 centimeter cubed graphite. So how many cups of tea, we're not talking Olympic-sized swimming pools here. We want to put that to one side. We're not even going to be going swimming until we've had our first tea of the day, are we? We can't consider doing anything until we've had our first tea of the day, by Jove. Right, so 1 mass of graphite is 1 centimeter cubed. Density of graphite, we can see the same equations. You get familiar with these equations. This number of moles, number of carbon atoms is this. Energy release per carbon atom is this. That leads us to this number of joules. So this is basically the same equation you saw above. Total energy released is this lot of joules. The energy required, Q cup, to heat 1 250 milliliter cup of tea by 80 degrees C. The mass of the tea, MT, of tea, is 250 grams, no less. Since 1 milliliter of tea has a mass of approximately 1 gram, like water, yeah, okay, a little bit more in there, but it's okay. The specific heat capacity of tea is the same as that of water, approximation. The temperature change is delta T is 80 degrees C. So the Q cup equals the mass of tea times the specific heat capacity of tea times the change in temperature we want to achieve is 83,680 joules. That's what we have to put in. This is why you should get a kettle where you can boil water and have a little amount in there. Or one where you have temperature settings. So if you want to have green tea and you want it at 70 degrees C, you can put it at 70 degrees C. For those coffee lovers out there, you can put it at 90 degrees C. You save a fantastic amount of energy because it takes a lot of energy to boil water, no less. Right, so the number, we're really getting to it now. The number of 250 milliliter cups of tea that can be heated by 80 degrees C with 1 centimeter cubed of synthesized CRERT, coherent energy transformed carbon from protons is 18,990,000. That's nearly 19,250 milliliter cups of tea. Now, why am I doing all this? I'm doing this because the normal jibe to people working in the field that I've been in for, well, basically since 2012. I'm into my 14th year here. Is, have you boiled a cup of tea yet? Well, we've already done much more than that in the system of Bin Juan Huang, but actually we haven't been boiling tea, we've been making hot water. But the energy released from just the production of 1 cc of graphite density carbon would brew us 19 million cups of tea. Now, this is where I'm going to get down to the hard facts, because you need to put this in context with how many teas the British drink. In the UK, according to www.tea.co.uk/about-tea, Brits drink about 36.5 billion cups of tea. Billion cups of tea, right? Per year. We would need to produce a cubic block of graphite density carbon of 12.43 centimeters per side. Ooh, the mercy. Oh, it's so terrible. That's like a grapefruit, a small grapefruit of carbon to brew all of that tea, weighing 4.34 kilograms. We're talking kilograms here. That's nearly the mass of 1 gallon of petrol. If you're looking at British gallons, not American gallons. It's nearly the mass of 1 gallon of petrol. That, my friends, is the amount of carbon we will be putting into the atmosphere by producing water to brew 36.5 billion cups of tea. To put that in context, we could produce 4,000 standard number 2 HB pencils with the waste carbon. 4,000. That could keep a primary school in pencils for a year. This is just terrible waste. Terrible waste. Look at the waste in that. Okay, I'm going to compare this to fission. If we are to use fission, let's compare this. Like, essentially, it's very, very easy to get the water fuel needed for CERT. Okay, we need to get enough water to produce, let's say, those 12.35 by 12.35 by 12.35 amount of carbon at the end of the day. Where can we get water from? It's a toughie. It's a toughie. However, the processed water is rich in the nutrients for agriculture. What do I mean by that? I mean literally the elements that this thing produces is the same elements that we need in agriculture. Let's show you here, in case you don't believe me. These elements here: phosphorus, sulfur, calcium, potassium, magnesium, iron. These are absolutely critical for soil health. The waste, the trace elements that are synthesized in this process, the wastewater you just put on your fields, and it will, in my view, enhance them. In contrast, according to the calculations below, you will need about 2.715 kilograms of pure uranium-235 to do the same heating. This requires just to source the uranium. 1.3 million liters of water and 95 megawatt hours of power to produce. And that is not considering the reprocessing and waste issues. That is to say, you produce really stupidly toxic waste and you burn your fuel in a typical nuclear rod from a concentration of, let's say, 5 or 4% down to 3%. And then you have to reprocess that. But just to produce the 2.715 kilograms of pure uranium-235, to produce the same hot water, you need to use 1/3 liters of water and 95 megawatt hours of power to make the actual fuel to start with. What you need to do to get the water, it depends if you're living in a desert or you're living in Iceland or Greenland. There's even more water in Greenland than there is in Iceland. It's like everywhere. It's frozen, you just chip a bit off. So that is mostly what I wanted to talk about today. There are some secondary kind of thoughts. Just want to check I've gone through everything I wanted to do here. Essentially what I've shown is that in this particular system, we can't consider the oxygen. Yes, often there's like 20, 30, 40% oxygen in that core. But because we have water in the system, we can't say for certain, and people will criticize you, that the oxygen was in the water. Not surprising you're seeing oxygen in the core. Okay? But the carbon and these other elements like phosphorus, you know, in the specific structures, the most likely reactions to produce phosphorus, the most likely reactions to produce 22 neon, the most likely reactions to produce 17 oxygen, the most likely, all of these things are the things that are observed in these structures and in the analysis of the water and the gas from the Binge-Wenhuang reactor. And the element isotopes that they produce typically are the most abundant isotopes in the periodic table, like 28 silicon, like 48 titanium, like 56 iron, like 32 sulfur. These are the things that it is most likely to produce. Okay, so let me just see if there's a whole other bunch of addendum points that I wanted to make, but I will ask some questions here in a second. Is there anything else I really wanted to say? Yeah, I mean, I talked about the fact that it's kind of like a non-thermal process. It's non-thermal on the outside, but there is fusion energy that caused the whole thing to swirl. And we can see that that can tear through matter. We can see transformations, for instance, in the Usharenko effect, where you have a structure that is boring 30 centimeters into steel, making a hollow channel, fully vitrified on the sides with transmuted material. We can see in the Hutchison effect, aluminium is glowing, and then you turn off the power, and Alec Pizarro could come over and leave his fingerprint in the aluminium. Okay, so it was able to be moved around. But interestingly, in some of the Hutchison effect and also in the event, when the fields are turned off, like for instance in his boat, you have these little sprites moving around like a plasma effect. And you can imagine what's happened in that situation is the interfering fields where the topological monopoles were being formed were doing the coherent energy transformation processes. The energy was building up in the coherent condensate in that topological monopole core and subcores. And when the interfering fields that were driving them and binding them in place collapse, they can't maintain the coherence, and the excess energy that comes out and it produces these little plasma jets. Okay. Similar things we saw in the Lion reactor with the manipulation of matter. You know, these structures are boring through silicon dioxide. We've seen it in Ken Shoulders, literally burrowing through matter. Here you can see here. If I can go, and it's actually going to show me here. You can see this is he calls this process non-thermal. Now, what Ken Shoulders describes when it's boring through this silicon carbide here is he's saying that it's giving the silicon carbide on the periphery of the exotic vacuum object extra electron, and so that it can't maintain the binding of the silicon carbide that it would ordinarily do in a solid state. And he calls it a non-thermal process. So you can see here, many of the effects are entirely different from are an entirely different form of non-thermal material dishevelment due to the peculiar properties of the bombarding entity. Yeah, so either a gradient of over 26,000 degrees per centigrade. So right, he's saying silicon carbide must have a certain temperature in order to fluidize it, and then it's fluidized, and between here and here, it's totally unaffected completely. We saw the same thing occurring on the HHO gas on the 10 yen coin. You have a very, very tight boundary, and he's arguing that there must be either a thermal gradient of 26,000 degrees per centigrade, or it's a non-thermal process. And I would argue that all of this fusion energy that's been generating and produces this intensification of the magnetohydrodynamics, and the self-similar substructures that go around the outside and come back in and go through, which are forming those apple-shaped structures, they are tearing through, and they are literally able to rip stuff apart. So it's to a degree, you could consider it mechanical, and you can see that in the presentation. For instance, if I go here and I go here, maybe here. No, I don't have it in there, but yeah, we had it where it has the copper on the outside of the structure, and it literally ripped copper from the metal sheet in a 90 micron area. And I don't think it's too dissimilar from this kind of scale here. Maybe it's even tighter than this. This is a 20 micron here. I think it was a 90 nanometer. So this might just be a splatter on the outside, and it's a really tight level here. But anyway, it says, to arrive at this number for the thermal gradient, I used very low melting point material for the silicon carbide binder and let the EV pass through the composite target. On one example, paraffin wax was used for the binder, and both colloidal graphite and silicon carbide were used as fuel in the two separate tests. The boreholes produced by the EV passage were so perfect that the cusp of the intersection between the dual EVs could be seen. This indicates that the entire 2,600 degree temperature drop occurred across less than 0.1 of a micrometer of space. Okay, there you go. It's exactly the same. Exactly the same. I estimated, and I'll see if I can find it, I estimated that the copper that's cut from the copper pipe on the outside of one of these apple-shaped structures was around about 90 nanometers, which is approximately the same as 100 nanometers, which is 0.1 of a micrometer. So what we observe in Binge-Wen Huang's reactor is essentially exactly the same. Let me see if I can find that. I don't know where I've got it now. Don't know whether I can find it now. Anyway, I'll put a link to. Yeah, if people can remember, maybe I'll go to the presentation. Right, if you can ask your questions now, I will answer where necessary. Let me see. I need to go to flux capacitors, don't I? So, I mean, the biggest thing is I want to reiterate that it has to be coherent matter in the core. For it to be coherent matter, and it comes out as a selection of atoms, it must be a series of coherent matter wavelets in there. And we know we can keep piling stuff in there and various amounts spew out. It is not particles bashing together. None of that is going on in this process. It might be when it comes out at high energy and those are colliding into other things, but really, because it's so divided between all of the atoms, they individually might not have a lot of energy when they come out in many instances, unless it's overdriven. And then you can have some interesting things going on. So I'm just looking at flux capacitor now. Okay, let me see if I can find the right bit now without it showing me adverts. Come on, it's going to show me adverts. Right, maybe I don't find it here. Oh yeah, here we go. So what I'm talking about here is an impact that came up here. It's a pair. One came down here. It split up, and that one came over here. I think it broke up over here, and this one is the one that's very, very interesting. It's actually in a different document, DHX2C, so maybe I can go and look at that. But I go and look at it here. So this is the copper on the outside here, and this is 20 microns across. So I determined, thank you very much, Skoggy, very much appreciated. You can see this wave pattern on the outside here. I determined that this is about 90 microns. And for the first time ever, I read it tonight that Ken Shoulder's determination of the interaction distance is about 100 microns here. So effectively, we are in agreement, and this is produced from an Evo gun, and what I'm showing you here is produced from cavitation. Do many cathedrals still play the organ? That wasn't the kind of question I was expecting, but they certainly do here in the city of Brno. And I had the pleasure of listening to my daughter singing in a recital because she was learning singing at the opera hall. And they did a recital in one of the cathedrals or churches here with an organ. And it was just really reminded me of being a choir boy. And it's just, if you've never done it before, you absolutely have to hear a proper organ recital in a church, ideally with vocals. So Skoggy is asking, what matter were we transmuting to form the carbon in these instances? I have argued, there's many ways to get to carbon. I have argued in this particular instance that if you start with protons, that is, and electrons in the form of protium, atomic hydrogen, that is a proton with an electron, which you can get from water or you can get from hydrogen, and you fuse those all together in a coherent matter process, you get this 87 point whatever million electron volts to convert 12 atomic hydrogens to one carbon 12 atom. And you get that energy. Hi, Malcolm. I see you're in the house. So why am I bothering to do this? Well, I said I like swimming and I like drinking tea. But I spoke to Binder and Huang, and Binder and Huang was looking for the next paper that we want to publish. And I said, well, we've got this huge resource of actual physical artifacts on the different reactor core materials and detritus collected from the cores. And let's see if we can't do a paper that explores the potential energy that's being gained from these things that we can physically observe. It's not speculation about, you know, what's going on. You can literally see. This is not guesswork. That is actually doing this work. You know, when we're looking at this, you know, oh no, there's an advert. Sorry about that. Before I get a copyright strike, gotta love these adverts. Yes, that is coming out of that. That is coming out of that. That is going into that. It's actually a copper slug going in with its tornado. Yeah, this is all spewing out of it. Okay, but I couldn't really use these kind of examples for calculating the potential number of structures we need to use, like this example here where the braid, because it's difficult to determine just exactly how much is in there. And all of these little white spots here are titanium. Like you can see here, the titanium in here is 17.55%. But the bits in between are carbon and oxygen. So, and one is a fusion of the other. So that's what I'm talking about with the matter wavelet interference. This would the actual titanium blobs are coherent matter wave interference between the coherent matter wave of, let's say, carbon-12 and the coherent matter wave of carbon-oxygen, in my viewpoint. So John 9279-J80, catchy. When you talk about all energy being the reduction in the distortion of the physical vacuum, how does this relate to the electric field that we know the vacuum is made of? Whatever, electric field, vibrations, whatever. Just all you need to know is the Casimir effect gives you this energy release when you're not when you squeeze out the energy that's trapped in the gap, and like just think of it. You don't need to go to that level. Just as I'm saying, plasma is more distorting. You condense that, gas is less distorting. You condense that, liquid is less distorting. Solid is less distorting. So as you cohering or condensing matter from one level to the other, there is a thermal vibrational release. And to a degree, that is in the kinetic energy of those particles. And so this is what I'm saying, is that this process is non-thermal in the sense that the kinetic energy of the particles coming in is kind of irrelevant, because one, they are the energy is shared between them, and then the phase is synchronized, and then all of that goes into the Borg in the core. So it isn't a process that necessarily releases thermal energy, but it might excite the core and change its de Broglie wavelength in there, the actual wavelength of the coherent matter in there. But because physically the separate matter waves of incoherent matter can occupy different space-time, they are distorting more of the physical vacuum. When those are in superposition in the condensate, they are distorting less of the whatever you think the environment is constructed of, and so it's kind of like creating a Casimir well that just matter can keep coming back down. You understand? Thank you very much, John. That's very kind of you for that donation. Really appreciate it. Yeah, so Elijah Coakley says it's asymmetric light pressure, and that's effectively what it is. But that some people get confused and think that light can only be visible light, but light is basically photons, and there are photons that are super long radio waves, extra low frequency waves, and there are photons that are gamma, and in theory, go higher. And the higher the frequency, the more energy it contains. And this is where the fantastic figures you get for the 0-point energy claims come from, is that, of course, you've got very, very high frequencies in there. And what I'm saying here is that we really need to brew a lot of tea. And, we don't want to, we're not doing it, in my view, using normal ideal gas law, because we're kind of breaking that to achieve our goal here by bringing things together and letting them decide what they want to be in a natural way. And I really believe that something along this line is why you can have transmutation in living things like chickens and like bacteria, with the examples I gave at the beginning with Alekor Lenova and Vladimir Vysotsky in the production of iron 57 from manganese 55 with heavy water, and the remediation of cesium-137 through barium-138 using syntrophic colonies of methogenic sea ooze, which is basically like a yeast, hydrocarbon and light water in the case of the remediation of cesium-137. And I've always, and I've spoken about this before, I wondered how people survived in concentration camps when they were just eating charcoal and water. And I think the body can get into a state where it can pretty much get a lot of what it needs from those things which seem impossible. That's very, very generous of you, Mark Dam. Really, really appreciate it. And it did take me a while to understand this phrase by Stoyan Sarg, but I was confident enough to use it within a few years of him saying it to me. And really where I'm at now, it just makes complete sense. And this system ability to create this Casimir well, as I'm referring it to, because you're able to condense so much matter into the same space-time that effectively it's kind of like gravity, and it is effectively a gravity beam. It's the same thing, because matter in the form of relative neutrinos and clusters thereof, they are dragged, and it's the clusters thereof, in my view, which light travels over, and that's photons of all energies. Therefore, this is effectively pulling Casimir. It's pulling 0-point energy into the core, and it keeps on doing it because it keeps cohering matter in there. And as the energy is pulled in, the energy just becomes a change in the overall wavelength of the coherent matter wavelets of the various element isotopes that are in there in this electron nucleus nuclei macrocluster that is in the core. So dark matter is playing a role in this in the form of relative neutrinos and condensates thereof, and all coming together in, and it's the electrodynamics of this that allows it to keep its virial stability on each fractal level, and that gives you your Casimir well. And as this builds up, it produces not only a magnetic core, but it's also a unification of the forces ultimately. And so you have a gradient not only of etheric pressure, of photonic pressure, you also have a great gradient of magnetic field and gravitational field. So it's all of the above. And that's why, in my view, it does everything from van der Waals forces to causing quark-gluon, magnetic disconfinement of baryons and to disassemble matter. I think what's really exciting for me is, I will be able to share with you a technology that was patented in Russia. It was never developed because Russia produced a lot of fertilizer. Fertilizer is considered potentially as a means by which people are exposed to too much radiation because of potassium being put into the ground or whatever, but I don't know. But this patent, which was expired, a Ukrainian guy, that's very kind of you, Yoni. This Ukrainian guy built this portable processor, and what it has in there, it has a cavitator and an arc discharge, and it produces water which you mix the bacteria from the soil that you want to work with in, and the bacteria go absolutely freaking mental in this water that's gone through a cavitation and an arc discharge process, which is essentially the same as the hydrowave system. Those two processes in water produce all of these bioavailable, newly synthesized elements. So the bacteria go absolutely skits, and you can keep dividing this water, and the bacteria will fix nitrogen from the air, and then you can spray this on the ground. And not only do you get the fixed nitrogen, the bacteria that's local to the actual bacteria that you have in your ground, you actually have this basically unlimited fertilizer. Which is self-replenishing, and it's bespoke to the soil that you are trying to fertilize, because it's from the bacteria flora that is there, fauna, whatever you would call it for bacteria. And so we know from like cavitated water and let's say from Alexander Shishkin, he puts that and sees better growth in plants. So I think the waste product from this process, which I believe, when it's done right, can produce significant extra thermal energy through this process. And when you understand how to manipulate the hydrodynamic shear, you can accentuate it, then I think the byproduct is extremely good for crops. Yeah, first order saying, yeah, cold plasma has been shown good for plant growth as well. Yeah, I mean, of course, plasma in the atmosphere is what fixes nitrogen in thunderstorms. And that's why my father, as a farmer, always said, there's nothing better than rain after a thunderstorm to water your crops. And I don't just think it's about the nitrogen that's fixed in there. I think there's other things like sulfur, potassium. I think some of these things will be synthesized in the same process. Technologically doing this to be able to produce that best water, and maybe even better than nature gives you on a regular basis, and have it right there for use on demand is just a magical thing. And to have it as a byproduct of the means by which you heat your water is just an added bonus. Of course, as Kladoff showed in his work between 1998 and 2003 when he died in his cavitation of destruction matter. If you recycle this stuff, you end up by producing more and more new elements, and after a while you end up producing elements that are not good for anything, right? And this was also what was found by the recycling cavitator of Leclerc. And so this wants to be a process where you run the water through maybe a couple of times and then cycle it out, and then it's rich in nutrients and nothing toxic. Ken Pratt said, Bob, did the nut-zoid bacteria have any detrimental effects on humans? I'm not sure what you're referring to there. I actually would like to speak to Michael Levin. Yeah, I think he's done some fantastic work. So yeah, I think that would be a great conversation. Am I in need of an isotopic chemist? Firstly, I have to apologize because a lot of people are reaching out to me. In fact, I'm going to look at a paper in a second. In fact, I'll look at it now. So I was sent an email a couple of days back, or over the Christmas break. I was sick as a dog over the break. It was not good. I was basically laid up all over the festive season. But I got this mail, and let me see if I can dig it up. I replied at length. I actually spent a whole day replying to the guy and then not had a response back. But anyway, I did get some response back by some other people in the Nuclear Authority in Europe and wanting to be my friend, which is all a bit weird. Let me see. Where are we? Where am I? Am I even here? Okay. Let me see if I can find this. Maybe I can't find it. Anyway, I will find it from the name of the paper. Let me do that. Excuse me whilst I talk to myself for a bit here. Okay. So, let me try this. Okay, so I won't show the email, but I will read it. The guy is called Luca Gambarale. He's an Italian researcher. He says, Dear Bob, I read with great pleasure your New Year's post about coherent energy transformation and the concept of matter acting as one through coherent states. I appreciate your wishes and hope you have a very happy and insightful 2026. I'd like to bring to your attention that I have been working for several decades on exactly the topic you raised in your message. At the University of Milan, the group of Giuliano Preparata, and for those that you don't know, Giuliano Preparata developed the coherent ground state of water. He's also the guy that the Preparata medal is based off, that is given out to people in the condensed matter nuclear science area. He says, of which I was part of during my undergraduate and doctoral studies. So he actually worked with Giuliano Preparata during his undergraduate and doctoral studies. He developed a complete theory of coherent quantum electrodynamics, CQED, which is the extension of electrodynamics in the limit of high charge density. The extension has the central result, the demonstration of the existence in high charge density systems of coherent quantum states that make a large number of atoms belong to a single quantum state, called precisely a coherent state. These states aggregate a large number of elementary systems, atoms, molecules, and ions into so-called coherence domains, with dimensions characterized by the particular type of electromagnetic interaction that binds them. The theory demonstrates that the presence of high charge density, we all know where we can get that, causes a phase transition that defines a new electrodynamic vacuum, not accessible in the absence of high density charges. Recently, I have developed, together with Giovanni Modenese, and I think Giovanni Modenese is the guy that worked on the anti-gravity work of what's the guy? The guy from Finland, who is actually Russian. That guy. Anyway, I'll remember his name. If you can remember in the chat, that would be great too. Anyway, the framework of CQED, the theory of coherent states of protons diffused in a metal matrix. So he's talking about lattice-assisted reactions, and he's talking about protons diffused through a metal lattice, showing how above a certain density threshold, protons or deuterons reorganize themselves, forming collections of coherent domains with diameters on the order of microns. Based on this calculation, he has rigorously demonstrated the possibility of producing ultra-slow neutrons within the metal matrix, forming sufficient coherent vibrational excitation. Also calculating the neutron production rate, which is perfectly in the range of what is observed experimentally. This calculation strictly falls within the theory of standard model of particle physics and conventional theoretical nuclear physics without requiring any new physical principle outside of the standard model. Inspired by the theoretical result, I set up an experiment to demonstrate the production of ultra-low momentum neutrons, starting from a neutral hydrogen loaded in titanium powders and subjected to vibrational excitations. Of course, we've known that if you get titanium and you smack it with a hammer or you put it in liquid nitrogen, you get neutrons, obtained through fast degassing. And in 2015, I visited the Russian plasma physics laboratory in northern Moscow, and there was Sergei Godin, and he showed me this gassing and degassing of titanium and excess heat being produced there. I've shared all those videos in the past. So, yeah. So this paper here, I think, is quite relevant. This is paper actually cites the paper that I did with Binja and Huang, somewhere down here in the citations here. Iwamura, Chelani, Srinivasan, Iwamura, Hoiki, Metzler, Formachev, Zamalov. This is his cavitation process using titanium deuteride. So, you smack titanium deuteride and you get, there we go, Huang, BJ, water can trigger nuclear reactions to produce energy and isotope gas. Okay, so there we go. So thank you for citing us, Mr. Gambarale and Giovanni Modenese. And I think the phrase I want to get from this is something kind of like I've been saying for quite some years now. Let me see if I can find the phrase that I want. Let's look for... Let's try gamma. Because he's going to... Is it gamma? No. Okay. Nope. Okay. What am I looking for? Okay, here we go. Right, so So he's talking about reactions here. Neutron plus an isotope of titanium goes to a heavier isotope of titanium, and that is excited, and then that decays with gamma, where the heavier isotope of titanium is an excited state of titanium. The reaction is also exothermic, releasing an approximately 1.5 mega electron volt photon. That's the gamma photon here. Finally, the production of tritium can be described by the following equation. Neutron plus deuterium goes to excited state tritium, and that releases a gamma, where the excited state of tritium and tritium are tritium nuclei in excited and ground states. In all these cases, the gamma rays produced by the de-excitation of the metastable state of the newly formed isotopes, denoted by an asterisk, that would normally be radiated away in the vacuum in the time frame of the order of T equals 10 to the minus 6 eV to the minus 1, which is equal to 10 to the minus 22 seconds, are not detected outside the host metallic matrix, matrix, because they are coherently absorbed by the coherent state of electrons present in the metal. There we go. So I'm arguing that the coherent matter wave structures in there, being the coherent electrons and the coherent matter waves of whatever elements are in the cores, do the same thing as he's arguing here. The coherent nature of this interaction implies an amplification factor for the electromagnetic coupling constant of the order of this, where Ne is the number of electrons in the coherent state, implying an amplification of the interaction probability of approximately 10 to the power 8. The gamma energy is thus distributed among a large number of electrons, so each acquires a small fraction of an electron volt, which can then be efficiently converted into thermal energy. The result is the absence of gamma emissions and an increase in the crystal's temperature due to the conversion of gamma into the heat. Now, I agree with the broad thrust of this. The difference between what he's got here is he's doing an idea of how the process is occurring, and he's saying that that is where the heat is coming from. And because you've got this coherent structure, which he's hypothesizing and calculating is in there, can capture the gamma ray rather than allowing it to be released. What I'm showing with the structures that we've observed across a broad range of different systems is the physical thing that is creating the coherent matter. Now, these can be of all different sizes and scales. It would appear that the smallest one needs to be around about 1 micron. Does he say anything else there? But anyway, he's basically saying the same kind of thing. Maybe I can see, let's see this one. What did he say? No. Anyway, that's the most important thing. Now, when I was looking through this paper, and he's focused on the production of tritium and so forth, and new isotopes of hydrogen, there's a reaction like his gas analysis here, and there was a meltdown in the reactor. He actually shows, he doesn't discuss this argon over here. And the argon here is showing it after meltdown and atmospheric, because it basically broke the reactor. I'm not showing it, am I? That's annoying. There's a breakdown in the reactor, and after the meltdown, you're seeing natural isotopes. So you've got the normal isotope here at 40, and then you've got 38 and 36 down here, and these are the very, very much lower, many orders of magnitude. But when the actual reactor is running here, you have a very incorrect isotopic ratio between the 36, 38, and 40 isotopes of argon. And he doesn't discuss this, but I wrote to him and discussed this, and I said, look, you can actually have reactions, and if I do it here now, you'll see what I'm talking about. Can I pull this up here? Yeah, okay. If you do reactions of titanium here, in a coherent matter sense, you get the synthesis of argon here in quite a few of these reactions. So, and if you look at it, the most energetic, that is to say, the one that I would expect to occur most often, produces argon 38 here. Then the next one produces argon 38, and then the next one produces argon 38, although that needs a neutrino. This one down here produces argon 38. This one 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 produces argon 38. Then you have an argon 40 down here, but 47, 49, you've probably got a reaction somewhere that's already producing argon, which is 47 and 49, I don't know, but 47's up here. What have we got? Yeah, so mostly 47 will be used up in this reaction. So my prediction would be that they would get a lot of argon 38 produced. And I think you have to go way, way down before you start to see argon 36. Argon 40 is there. Argon 36 is way, way down here. Okay, and I think there's reactions with 46 and 47 that produce argon 38. So when you look at his data here, you can see that if I go and look at the natural ratio of argon, maybe, I think then the natural ratio of argon is 99.6% is 40, right? So, and argon 38 is just 0.06. In fact, it's the most rare form of argon. And you can see that down here, this is true of the meltdown, but in the actual experiment here, you've got, what is it? That's just one order of magnitude is down there. So this isn't even one order of magnitude higher. And it's over 3 orders of magnitude. So the normal ratio of argon 40 to 38 should be 1,581. So it's 3 orders of magnitude, over 3 orders of magnitude higher, which is correctly represented after the reactor leaked. But in the reactor and when it's operating, you're getting this very, it's not even 1 order of magnitude between the two. Therefore, there is a massive, massive discrepancy here. And I'm arguing that that is from reactions of titanium and titanium. And this kind of reactions occurred in Leonid Arutsyev's work with titanium and so forth. So if that's true, then other elements can be synthesized in that process. And I looked at some. What are we seeing in this titanium-titanium reactions? Well, we're seeing sulfur formed and iron formed and calcium formed, and all of these kind of things were produced in the work of Spectrum of Ball Lightning by Leonid Arutsyv. So in his exploding titanium foil in water, and you can see that the isotopes of titanium changed, and he saw these elements being synthesized. Iron, nickel, chrome, these kind of things being synthesized here. What have we got here? We've got iron, nickel, and chrome. They're the top 3 things. Iron, nickel, chrome, iron, nickel, chrome. And he's got calcium and sulfur, and we've got calcium. I don't see sulfur there. But anyway. So this is a completely different story from the one that he's trying to talk about, which is hydrogen interactions. And I'm saying I think something a little bit more interesting is going on, and your argon signal is pointing that out. Anyway, maybe that's why he didn't write back to me. Okay, so I'm going to see if there's any more questions. Great to see you here, Crypto Alchemist. Yes, probably. Maybe I've explained it. I don't know. Thanks very much for those huge donations today. It really, really makes a difference. Thank you so much. Okay, so I'm going to run through. Hello. Right, I'm going to just run through the main presentation. So, this was O'Day Brewing Tea by breaking the ideal gas law. The ideal gas law is very well known. It's taught at high school. And normally PV is a constant. And the temperature is related to the proportionality with the product of the pressure and volume, and inversely with the amount of gas. And this gives you things like heat pumps and refrigerators, and when you spray a can of gas, the can cools down or the spray can cool, these kind of things. And I talked about Stoyan Sarg's comment to me, which I took on board: all energy release comes from a reduction of the distortion of the physical vacuum. And I talked about Casimir well concept, which I've been trying to get across for some time now, where matter is pulled by this vortex into this core, and the properties of the structure force coherence in here, such that you get a unification of the forces, and the Aharonov bomb effect causes the matter isotopes and electrons, let's say, to form an electron nucleus nucleon macrocluster in here. That is the phrase of S.V. Adamenko, proven technology by the US fusion program since it was transferred from Kiev in the 2010s and verified in up to 2017 before being, would appear, classified. And so you have a gradient of the 0 point in here of dark matter, of photonic pressure, of magnetic field, and effectively you get a unification of the forces in here. And when you get enough coherent matter in there, I believe you have coherent energy transformations going on. All of the magic can occur that we see in all of these different systems, which have been inadequately explained. And protons are some of the best way to get there. Oxygen's great, but protons are good too, since it has this wonderful nuclear magnetic moment, and as I explained in Defying Gravity, protons aligned, in my view, will create this equivalent of the ferrite core in an electromagnet. It will enhance the gravitational condensation process, driven process, to generate better coherent matter wavelets. The overall electrodynamics of the fractal MHD, fractal toroidal moment structure, uses the AB effect to force coherence and produce a matter wave condensate. And the thing is non-thermal kind of on the outside when it's kind of like forming. And because the matter is condensing into the coherent matter in the core, there's no typical pressure increase that would otherwise destabilize this structure, because it's forming this coherent matter. And you can have the superposition of these matter wavelets. High matter densities can be achieved, and while the structure remains stable. All energy is shared between all members of the condensate, maintaining coherence. And this is supported by Luca Gambarale and Giovanni Modadese's latest thinking. And these are the people that have taken the torch of Giuliano Preparata. And so I do concur with a lot of the thinking when you are referring to the energy of collapsing or electronuclear collapse being shared within the condensate, rather than being ejected as vibrations in the radial neutrino condensates in the environment around. Ultimately, you're effectively getting highly energetic proto-matter in this core, which is then electronuclear regenerated when the fields collapse. That is, the fields that are forcing the coherence and the phase singularity. When they are unable to do that AB effect and unable to keep the matter in that core, then whatever's the state of play in there when you switch off the lights and the matter comes out again, it decoheres. But it may be new atoms and they may be at a different temperature kinetically. And so, but because all of the energy generated in the balance of the matter that is there is shared equally, exactly, between each of the matter wavelet packets that are released, then none of it is too energetic such that it does more than do thermal interactions with the environment for the most part. So the original reaction pathway, I said the key reaction was proton and oxygen 16, or hydrogen and oxygen 16. The most abundant isotopes in normal water form oxygen 17. And the reaction was this, based on Parkhomov theory. And there are other ways to get neutrons to do this, but it's unnecessary when you use Parkhomov theory because the matter waves in the core can interact with radial neutrinos, and the radial neutrinos and clusters thereof can be pulled in via the toroidal moment or anapole, depending on whether you're talking about radial neutrino or clusters thereof, and affect this transmutation, which has a net yield. And so you don't need to worry about producing the neutrons separately. And in fact, I would argue vast numbers of nuclei simultaneously transmute, and the balance energy is shared between the condensate that's resulting, or the wavelet packets that are resulting. So I don't know whether any of these are necessary, but they're just ways that people think about them. And so once you've got your oxygen 17, the first most likely coherent matter wave process is not this one down here, because it has a very, very much smaller reduction in the distortion of the physical vacuum. This one has a much larger reduction in the distortion of the physical vacuum. And so I predicted that the carbon 12 would produce neon, and in fact it turns out he found neon 22 in the absence of 21 or 20. And so the most likely reaction is the one that was observed in reality. I predicted this in 2022, observed this in 2024. It has a lot of phosphorus on the outside, and in the core it has a lot of silicon and phosphorus. And so weirdly, it would appear that when you have the most abundant isotopes of oxygen in a coherent energy transformation process, it produces helium-4, which is also observed in the Huang reactors, and silicon-28, the most abundant element isotope of silicon, produces this. The next coherent energy transformation process that starts with oxygen 16 produces a proton and a phosphorus-31. Phosphorus is only a single isotope anyway, and this energy of 7.68 million electron volts will be shared between these two, and the proton there is been born in the electron nucleus nuclei macro cluster in the core. And so this energy of this particle may just become part of the overall structure, and that might trigger the onward progression of reactions. So I think this is a first most important reaction in order to trigger the process. Now, Huang, I predicted there would be some iron-rich granulated spheres, and surely there was, and they were hollow and they broke open, and inside we saw fusion of matter to titanium, which is CO2, and going through the reactions then to see the rest of the potential outcomes. 217 oxygens goes to sulfur 34. 2 sulfur 34, so this is a coherent energy transformation to sulfur 34. Two sulfur 34s goes to iron 56 and carbon 12. This was my explanation way back when on ODE HHO. But effectively, you can see that that is really just 4 oxygen 17s coming together to produce this output. You can get there by using the neon 22 and the sulfur 34. So all of these are the most likely outcomes, and they end up producing the most likely elements that you see. Okay, so this was my revisiting the 1994 paper of Sundaresan and Bokris, and the energy output was basically the same, and I believe that they would have seen these structures had they looked. Now, in the Huang reactor to get titanium, you can look at this product that is there and this product that is there, and that gets you the most abundant element. So this is my first most likely product to be synthesized from protons and the most abundant hydrogen and oxygen. And this is from just oxygen and oxygen interactions. And so effectively you could view titanium as a wavelet interaction product. And there's no kind of particle interactions going on. It's just all of the coherent matter condensates are interacting, and a proportion of them, when the matter wave collapses, just happens to be titanium-48 and other isotopes. You need to completely rethink how the process is occurring internally. So Adamenko, this is in his 2003 patent, and he says in this iron and silicon blob that's formed out of pure copper and electricity, and I think hydrogen in the atmosphere there, you end up with the matter being synthesized in the hollow area by way of dark matter. And then I'm just viewing this now as just coherent matter wave interactions of just protons. And so there's a whole bunch of protons here. The way to think about it stepwise, you get the energy release, which is 2 protons goes to 2 deuterons, 2 deuterons go to 4 helium. A deuteron combines with 4 helium, so that would be effectively 3 deuterons, leaves you with lithium-6, and then 2 lithium-6 goes to carbon-12. And the overall energy release of that whole process is 87.468. And if you double that up, you get 174.936 MeV shared between 2 carbon atoms, and they would come out and they would energetically interact with the carbon condensate that's progressively forming in and around the core. Overall activation energy could be triggered by this initial coherent energy transformation process. We know these products are produced, so this is quite a viable outcome. So this initial reaction, R0, initial energy comes from R0 inside the core, and AB effect enforces coherence, that is, with the energy that's released. Producing 1 atom of carbon via CERT yields 87.468, and Huang's best reactor, to raise that 60 liters to 80 degrees C, you need basically a cube of carbon synthesized of 233 micrometers. And based on actual structures that look like they've come out of the inside of a active agent, this magnetohydrodynamic structure, which has, in this case, 67.03% of atoms of carbon. We can calculate, based on this being this 20 micron by 20 micron structure, and assuming it's not 67.03 but 50% carbon, a density of graphite using actual imagery from the inside reactor core. I'm only looking at one side, not the outer inside of the outside. I'm just looking at the outside of the inside, and based on the area and based on a very, very conservative approximation, we need very, very little pipe length to produce the energy, assuming that the carbon was produced through this methodology. And then I did some little fun equations here, which I will share. And I'd like to make this part of a little bit of a fun paper. Doing the transformation reactions from atomic mass of the starting atomic hydrogen and the end carbon, you get almost exactly the same energy as comes from the reaction calculators, the MFMP Parkhomov reaction calculators. And so we're in agreement there. This is the full calculation to work out the side length of 233 microns. And then let's say we're only making 1 centimeter a third. We worked out that we could heat comfortably 10 Olympic-sized swimming pools, but more importantly, we could make from 1 centimeter of graphite, we could brew up 19 million cups of tea, and from 12.43 centimeters per side of graphite produced, we could produce all of the tea for the UK for 1 year. And that if this process is verified and realizable in practical form, it's far, far better, not only because the fuel is water, but because the waste product is good nutrients for agriculture, and the water is just water. You don't need to process it to make it into the fuel, it already is, whereas you need to use vast quantities of water and vast quantities of power just to produce the fuel, let alone making the reactor and processing the waste and dealing with the nuclear waste afterwards for using fission processes. So I commend to you that brewing tea by synthesizing carbon by way of coherent energy transformation processes is a much, much better way of doing it. And with that, I'll say thank you very much for your time, and I will see you in the next video.